activation energy problems or application of the Arrhenius equation. If we want to look at the forms of the Arrhenius equation, this form that Zumdahl first presents, and any author first presents, is really, in my experience, very rarely utilized. We're going to use these two forms. This form I would only rely upon if we are given a rate constant at one temperature and we're looking for a rate constant at another temperature, or the temperature of a new rate constant, or you're given those criteria, a rate constant and a temperature, and another rate constant at another temperature, and you're looking for activation energy. So we're going to really probably rely upon this form of the equation most. If we look back at the example problems that I gave us in class, this first example tells us a reaction has this rate constant at this temperature and an activation energy of this. It's then asking what is the value of a rate constant at a new temperature. So we're going to use that third form of the equation, and there's my work there. What I chose to do is, instead of doing the anti-natural log or inverse or whatever language you guys are using, I chose to go ahead and express that as a subtraction of natural logs and then derive your answer. Now, I have this starred little item here. It's really something because with natural logs, depending upon how you adjust for sig figs as you go, that's really going to determine how many sig figs your answer has. So I'll know the range of possibilities that you should get for your answer. So as long as you're getting approximately close to 5.60 in per second or per second, you're more than fine. Okay, in this next example, we're given the reaction. We're told it's first order. But then we're told the rate constant was determined at various temperatures and a graph of natural log of K versus inverse temperature was constructed. So that's where we're graphing the y equals mx plus b for the Arrhenius equation, if we want to look here. Yeah. So we're graphing this y. Our slope will be activation energy divided by r, and the inverse temperature. Now, our y-intercept will be the natural log of a. So if we go back to see what we're asked for, we're told the slope. The slope is the negative activation energy over r. So if we take that times r, we'll get our activation energy. The y-intercept is the natural log of a, your frequency factor. Excuse me. So if you do the inverse natural log or anti-natural log of 38, then you'll get your frequency factor. So we've already answered how we get a and b, and then we, knowing those, can get the value of k. And if we want to just look at what I've done here, so our slope is activation energy over r negative. The frequency factor will be the natural log of 38. Sorry about that. Frequency factor will end up being this. Your activation energy will end up being that. Then once you have that information, you can go ahead and solve for your k using that y equals mx plus b graph. Then in the third problem, you are given the rate constant at a certain temperature, rate at another. You're going to find the activation energy, and then find the rate constant at a new temperature. So if we want to just go down, and please feel free to pause to take a look at my work. What I got was the activation energy is 1.7 times 10 to the 5th joule per mole. And that is my value for the K. And to share the answer for 4, it's 83 kilojoules per mole. We are given that the rate triples when the temperature is increased from 25 to 35. So we're given the ratio that we can apply directly to K. Directly to K. If the rate is tripling, well, we can go ahead and say that K2 will be 3 times what K1 was. arbiters, we can then solve for activation energy. Please feel free to rewind, pause. I hope that you can read the Chicken Scratch, which is my work, and I will address any questions you have on any of this